verifications we are going to do it. So there are varieties of levels are there for the testing of the silicon wafers. So we call it as a testing of a chip that can offer in a different levels also. So the first level we call it as a wafer level, the second level we call it as a packed chip level, and the third level we call it as a board level, and the next level we call it as a system level, and the last level we call it as a field level. So what you mean by wafer level is, so when you do the fabrication, so we discussed about the fabrication of N-well process and the fabrication of the P-well process. When we do the fabrication of any basic elements, that is nothing but through the use of silicon wafer. So if there is any defects are there in the fabrication of the silicon wafer itself means, then whatever the circuit we are going to implement through those defected wafers will directly affect over the performance of the design of a VLSI subsystem. So therefore, it is necessary for us to do the diagnosing or the verification process at the initial stage itself. So that we call it as a wafer level verification. So in the wafer level verifications, we make sure that what thickness we have selected, it is according to our design. If there is any defects are there in the wafer itself means, then we need to replace with a fresh and a very clean wafer, so that because the fundamental elements whatever we are going to use for the implementation of the logical circuits, so that only the performance will depends upon. So therefore when we select the fundamental elements, that is nothing but the metals, the polysilicon what we are going to use, and also the wafer what we are going to use for the fabrication of, it may be NMOS transistor or it may be PMOS transistor. So that plays an important role. So that has to be thoroughly understood and it has to be designed. So that we call it as a wafer level. So the second one we call it as a packed chip level. The second one we call it as a packed chip level. So once you have the verification of your design has been done successfully, and then the IC whatever we have done, it has to be converted into a chip, or it has to be replaced onto the chip. So how you are going to replace onto the chip? When you are going to replace your entire IC over the packed chip level well, so there also you should do the contact cuts, how we are going to replace this, because in the packed chip level what we do is the raw IC what we are going to already have a fabricated, so that has to have a communication with the packed pins which we are going to use it. So therefore in a packed chip level, so the communication between each pins what we are going to use for the design of any chip, so that has to be considered in a packed chip level. And the next one we call it as a board level. So in the board level means we have implemented a circuit diagram and the verification it has to be done now. So then we are going to represent in the form of boards, and we give a desirable input sections, and for the desirable input sections we will be getting the output. So that we call it as a board levels. The next one we call it as a system level. So in the case of system level, so we have done all the fabrications and all the setup has been initiated once the design of the chip has been done. And the next one is when we want to check for the functionalities of any application, or when we want to check the functionalities of any working principle, then we need to check the entire system. So that verification level we call it as a system level. And the last one is a field level. Yes, you have designed the chip and it has been tested properly in the manufacturing field. When it goes to the field level, so means where exactly it has to work. So in that environment, if your chip whatever you have designed, if it is providing a desirable output, or it is working fine for the environment in which the chip has been placed, so that we call it as a field level verification. So in all these steps, or in all the mechanisms, the verification at each steps also plays an important role in order to measure the performance of the VLSI subsystem. So and after that, for each processes, so basically we are going to do the implementation of the code over the chip. So when you write a code, so how you debug and how you are going to do the verification, if there is any fault happens in the during the generation of the code itself means, then that form of verification or that form of representation we call it as a logical verification test. So we undergone the test harness, that is the test bench creation, for in order to see whether we are going to get the desirable output for the different cases, and then we went for the regression testing. And in the regression testing, what we are going to use is, so we are going to use the different scripts which we are going to written in a high level language, we will be used in order to run larger test benches. Okay, and this regression testing which involved in performing the simulations that can automatically verify some of the functionalities which are directly converted or indirectly connected to the each module, so that will be responsible for the regression testing. And during the design part, what one common practice what we are going to do is, so when we run any program, we will be running this regression scripts also at every instant of time, so that if there is any changes or if there is any undesirable features we are getting from the subsystem what we have designed, so there only it enables us to have a corrective measurement. So that form of testing we call it as a regression testing. And the next we studied about a version control. Okay, so this version control, it is basically, it is a combination of your regression testing along with the versioning. So okay, what do you mean by versioning? Because as we add different applications, there has to be modifications has to be done in the code, and those modifications we are going to represent it in terms of versions values. So let it nothing but 2.0, 2.1 version, Xilinx 9.1i and Xilinx 9.12. So like that we will be having a different versions. So based upon the versions, we can able to see what are the different features which has been added to the subsystem. In those versions we are going to second. And the next one we studied about the bug tracking. So what do you mean by bug tracking is, so it is nothing but it is a unique or a Linux based management tool which will allow us to find varieties of bugs in our VLSI system design entity. Okay, it is nothing but it is a Unix or a Linux based management tool which will provide a varieties of bugs. So each system bug which has been entered over the system what we have designed, so we are going to find it out where exactly the bug has been created, and what is the type of the nature that is a bug has been created, and what is the severity of the bug whatever we have noticed during the execution. So all those analysis will be done through the use of this bug tracking software. Okay, and whenever a bug has been discovered, so a person will be responsible to analyze what is the type of the bug it has been created and what is the severity level that it can affect the performance of the VLSI subsystem, and has to be studied through the use of this bug tracking mechanism. And then we went for the manufacturing of text principles we went. So what you mean by manufacturing text principle is that in all the VLSI subsystem whatever we have designed, so it is necessary for us to incorporate the testing circuits. It is necessary for us to incorporate the testing circuit. Why? Because it proceeds us to have a concurrently with the architectures what we are going to consider. It enables us to have a concurrency in the architecture whatever we have considered, and the main purpose of this manufacturing testing is to screen out most of the defective parts before they are shipped to the customer. So as I discussed in the earlier classes or in the last class, so the manufacturing test, whatever we are going to do it in order to screen out or in order to segregate the defective parts which are there before we deliver the end product to the customer. So how we are going to do that? We are going to do that through the use of the analysis of the fault models. So we have some fault models are there, some predefined fault models are there depending upon the applications what we have generated. So based upon the applications what we have generated, so we will be using the different kinds of fault models. So basically what you mean by this fault model is, so they will analyze the various functionalities within the block, and if there is any fault is generated means that will be highlighted through the use of this fault models. Okay, so since it enables us to provide a faults within the circuits what we have implemented, so therefore we call it as a fault model. Therefore we call them as a text patterns as a fault models. Okay, so there are different types of fault models we have. So the first one we call it as a stuck at model. We call it as a first model as a stuck at model we call it as, and one more model we have the short circuit or open model, open circuit model we have. Okay, and those things yesterday we have discussed. So the first one we call it as a stuck at faults, the stuck at 0 or a stuck at 1 model we have. So in the stuck model, basically what we are going to do is a faulty gate input is modeled as a stuck at 0. If the gate whatever we have used in the implementation of a basic element, if it is fault has been generated in the gate level means, or in the gate terminal means, and that we call it as a stuck at 0 model, or stuck at 0 model we call it as. Okay, so depending upon the fault what it has been generated in the gate level, either it may be stuck at 0 or it may be stuck at 1. Okay, so what it does, it describes. Okay, stuck at 0 I understood and stuck at 1 I understood. So what it describes, it describes the board level design. So what is the board level we have designed, and it will design us, it will enable us to determine the adequate number of modeling faults. It will enables us to identify the adequate number of modeling faults. Okay, so there are two types of stuck at fault models we will be getting. The first one we call it as a stuck at 1 model, and the second one we call it as a stuck at 1 model. So depending upon the logical values, the gate which is not able to transmit from input terminal to the output terminal, so based upon that we may get a stuck at 1, means the output will be stuck to 1 only, it will not change for the particular input combinations. The output has to change from 1 to 0, but if your gate is not triggered properly means, then the output will be remained high even though the subsequent input changes. So that mechanism we call it as a stuck at 1 model. Similarly, stuck at 0 is for the certain input signaling methods whatever we are going to pass for the VLSI subsystem, the output has to shift, or the transition shift switch, the output has to switch from 0 to 1 or 1 to 0. In the case of stuck at 0 model, so it will be, the output will be stick on to the 0 level only, even though the subsequent inputs will changes, so that the output has to shift from 0 to 1 because of the infunctionality or because of the defects in the gate level manufacturing process. The output may not switch from 0 to 1, and that we call it as a stuck at model, or a stuck at 0 model we are going to call it. And one more type of the fault model what we have going to generate, or what we are going to use in the VLSI subsystem is the short circuit and the open circuit faults. The short circuit or an open circuit faults. Okay, so you can see in the diagram the shortened faults, we call it as a two bridge faults also. We call it as a shortened faults, as a two bridge faults also we call it as. So which has been depicted in the bridge diagram. You can see here the shortage of the two terminal, that is, it may be gate to gate, it may be drain to drain for the PMOS, or it may be the same thing for the NMOS also. It may be drain to drain connection, or it may be source to source connection. So such a mechanism we call it as a shortened, or it is also called as a two bridge faults, as you can see in the diagram. So here in the S1, the short S1 will result in stuck at 0 fault at the input. So you can see here for the S1, we are talking about the S1, the shorted fault. The short S1 will result in a stuck at 0 fault at the input terminal. Similarly, the short S2, which will modify the functionality of the gate terminal. Similarly, the short S2, whatever we have done, right? So if there is a short circuit is happening between the that is the drain of the PMOS to the source of the NMOS means, then that short we call it as a shortened stuck at 1 method. And because of this stuck at 1 method, the functionalities of the gate will changes. and it also ensures that the accurate modeling of the fault at the transistor level. It also ensures us to have a accurate modeling of the faults at the transistor level. So for example, if we consider a simple NAND gate, for example, if we consider a simple NAND gate, the intermediate node between the series of NMOS transistor is hidden by the schematic diagram. Okay, so what do you mean by this? So it is nothing but when we use the implementation of the NAND gate by using CMOS technology, the intermediate nodes which we are going to use in between the series of NMOS transistors, it will be hidden from the schematic diagram, and that we call it as a short circuit fault. And in the case of NOR gate, we need to have an addition of the two or more ORing, and it has to be take a complement of that. In such a cases, we will be getting a open circuit fault. And one important particular problem that will be arises when we go for the VLSI, that is CMOS technology implementation, is that it is possible for us to have a fault to the combination circuits also and for the sequential circuit also. Okay, so means what? In the CMOS VLSI technology, it is not only we will be getting the faults for the combinational circuits also, we will be getting the faults for the sequential circuits also, and by using this open circuit and short circuits, we can able to convert the combinational faults into sequential faults through the use of this short circuit or a open circuit faults. We can able to do it. Okay, so this is related to the open circuit and a short circuit fault. So you can see in the diagram, of course it is a combination circuit fault, that is nothing but it is a NAND gate, NOR gate implementations whatever we have used, and this NOR gate implementation we can able to convert them into a sequential circuit with the use of this bottom line diagram. Okay, so that is the beauty of your open circuit or a short circuit fault model. Okay, so these are the things what we have discussed in the next yesterday's class. So this is the defect, how we can able to create a static IDD current because of the short VDD between the connecting wires of the powering signals to your main circuit. So there also there will be a defect will be introduced in the static current which is flowing across the transistor element. So that has to be also taken care during the open circuit or a short circuit fault model detection. Okay, and